When you heat up liquids, they expand. So let's talk a little bit about thermal expansion in liquids. In particular, what we'll do in this video is we'll compare the properties of liquids with that of a solid from thermal expansion point of view. Now, if we go back to solids, we have already defined a number called as alpha L, the linear expansion coefficient. This number just tells us how much is the change in length of any given solid per unit length per unit temperature change. And similarly, if you want to calculate the changes in area, we define a very similar quantity called as alpha A. This tells you how much is the change in area per temperature change, per unit temperature change. And similarly, volume expansion coefficient alpha V. So we have three numbers that we can define for solids: one for length, one for area, and one for volume. And if you require more clarity on this, then we have spoken a lot about this in previous videos. So it would be a great idea to go back there, watch them, and then come back over here. However, when it comes to liquids, we don't have alpha L, we don't have alpha A, we only have alpha V. We can only define volume expansion coefficient. And here's the reason why. Suppose you have some container with water, let's say. It already has some water in it. And if you were to pour this water in, say, another container, say a test tube, let's say, the same water, pour another container, then notice that its shape changes. You may have already learned this. The shape of a liquid depends on the shape of the container, which means the length of the liquid or the height of the liquid, or maybe the radius of the cross section, or maybe the area of cross section, or total surface area. Anything you take, it turns out it depends on the shape of the container. None of these are fixed values. And therefore, you can change the area or the length of a liquid even without changing the temperature. Even by keeping temperature fixed, you can just change the container and these things change. So it makes no sense to talk about linear expansion or area expansion coefficients because the length or area is not a fixed value at all. But what is fixed for a liquid is its volume. Even if you change the shape, even if you change the container, the volume is something that never changes. If you want to change the volume of a liquid, there's only one way to do that. That is by changing the temperature. And therefore, for liquids, the only number we're going to talk about is the volume expansion coefficient. So let's just write that down. That's an important difference we can see. So for liquids only have volume expansion coefficient. Volume expansion coefficient. And the way we define this number is identical to how we do it for solids. The way we do it for solids is we define alpha V as change in volume per unit volume per unit temperature change. Identical. Again, if you require more clarity on this, if this seems a little bit confusing to you, again, go back and watch videos on volume expansions in solid, and then you can come back over here. All right, let me show you a table now. Here it is. Now, if you've seen previous videos, then you may have seen these values before. These are alpha L and alpha V values of some solids, but now we have also added in liquids, alcohol, mercury, water, and look, they don't have any linear expansion coefficient values. Just now we discussed, they only have volume expansion coefficients. We also have a gas, and you can see a couple of question marks over here. That's because gases are extremely interesting. They have their own story, and so we'll do that in another video. So let's not worry about them over here. But another thing which we can see from this table is that look at the values of alpha V. They are incredibly large compared to that of solids. They are huge. So that's another thing we can note. This means that when you heat liquids, they expand much more in volume compared to solids. So we could say liquids. liquids expand more than solids. All right, so let's look at water, for example. It tells us the expansion coefficient is 200 times 10 to the minus 6 Kelvin inverse. What does that mean? What that means is if you take, say, 1 liter of water, visualize this, take 1 liter of water and you increase its temperature by 1 Kelvin, that's why the per candle, 1 Kelvin, then the delta V, the change in volume, would be 200 times 10 power minus 6 liters. And if you convert that, that's about 0.2 milliliters. So 1 liter water, increase temperature by 1 Kelvin, it'll expand by 0.2 milliliters, which doesn't seem like a lot. It is very tiny, but it's much bigger than what solids would give you. And therefore, if you want to build a thermometer, the best way to do that is to take a liquid and put it inside glass. Because notice, glass doesn't expand much on heating. And therefore, when temperature changes, the glass hardly expands. But say the mercury, which we usually use, expands a lot. And so we can easily calculate the temperature by using mercury inside a glass. But look at the value of alpha V for alcohol. It's significantly higher than that of mercury. Which means if you were to put alcohol inside glass, that would be even better thermometers. And we use that. Chances are that the thermometer that you may have used in your school laboratories are indeed alcohol thermometers. And there are many reasons for that. One is that it's much cheaper to make an alcohol thermometer compared to mercury, so it's readily available. Another reason could be that since alcohol expands more, it's more thermally sensitive, and so you can read temperatures better with alcohol. But I think the most important reason for me would be that mercury is poisonous. So if the thermometer were to leak out, or maybe it were to break, and laboratory thermometers are bound to break. I mean, I as a kid used to break them all the time. So anyways, if they were to break and if you were to inhale the mercury vapors, that could be very poisonous. And so the safest option for laboratory thermometers would be alcohol thermometers. Alcohol has one disadvantage as a thermometer. Alcohol boils at 80 degrees Celsius. So if you need a thermometer that can measure very high temperatures, we usually go for mercury thermometers. But for low temperature measurement, alcohol thermometers are the best options. And so even the clinical thermometers, the one that you stick into your mouth to check your body temperature when you are running a fever, I'm not talking about the digital thermometers, not those. I'm still talking about the liquid thermometers that we used to use before. Those thermometers are also alcohol and not mercury. It makes sense, right? I mean, who would want to have a glass tube filled with poisonous liquid in their mouth, especially when they're sick?